we get that. So we need to first find the uncertainty in our average pressure and the uncertainty in our change in volume, right? Which aren't going to be that easy to do. And then once we have those uncertainties, well, then we can worry about the work. So I think the change in volume one's easier. So let me start there.
I just had a question. The change in volume is much smaller than me.
Okay.
Did you convert it from 1 milliliter, or did you convert it to cubic centimeters?
A cubic centimeter and a milliliter are the exact same thing. If you are changing cubic centimeters to cubic meters, you have to cube the conversion factor.
Oh,
right? So either way, we're altering it by a milliliter. All right? So I'm going to do the change in volume uncertainty first. And when we find the change in volume, we are subtracting these two values. So when we're subtracting or adding, we add the absolute uncertainties together. All right? So the absolute uncertainty for the initial volume was 1 milliliter, and for the final volume was 1 milliliter. So the absolute uncertainty for delta V is 1 milliliter, which is the same thing as 1 times 10 to the negative 6 meters cubed. So the change in volume really is negative 6 times 10 to the negative 6 meters cubed plus or minus 1. No, 2, not 1, 2 times 10 to the negative 6 meters cubed. And that makes sense because this one could be as large as 15, this one could be as small as 7. Right? So really the difference could be as large as 8, which is what this is telling me. All right, questions from anybody on finding the absolute uncertainty in the delta V? I don't think we've really had an official, prescribed method in what to do when we're averaging values together in terms of the uncertainty. I think there are a number of different, probably equally inappropriate ways to handle it. What I'm going to do is say, hey, we are adding these, so let's add the absolute uncertainties together, right? So 0.5 kilopascals, 0.5 kilopascals, boom, that's 1 kilopascal, or 1,000 pascals. So I've run out of room. I'm going to rewrite this up here. So the average pressure is 135,600, if I round it, pascals, but plus or minus 1,000 pascals. And those precisions are not the same. So that does make me have to round this to 136,000. All right? So I'm saying that the absolute uncertainty in the average pressure is 136,000 plus or minus 1,000 pascals. Right? Other people would actually say it's 500, right? And they could be equally wrong or right, whatever. Follow-up questions on my maybe simplistic way of reporting the uncertainty in the average pressure. All right. So now we have to bring those two uncertainties together to find out how much uncertainty is in the work. So Jake said he's going to have no problem doing this because of his review video for the seniors. So what do I have to do?
You have to do percent uncertainties when you're multiplying and dividing.
I can do percent uncertainties. I also can do relative uncertainties. And I'm going to do that just because it saves me a little bit of work if I find the relative uncertainties. So yeah, that's exactly what I'm going to do. At this point, again, I kind of need extra room, so I'm just going to erase my raw data. And let me find the relative uncertainty in the pressure first. Relative uncertainty is the absolute uncertainty divided by the value. Okay, so that will give me the relative uncertainty in the pressure. The relative uncertainty in the change in volume would be that absolute uncertainty, 2 times 10 to the negative 6, divided by the value. It doesn't actually matter if it's negative or positive. There's 6 times 10 to the negative 6th. All right, and then if I add those two relative uncertainties together, that will give me the relative uncertainty in the work. All right, so let me replace both of those with decimals. This one I'm pretty sure is just like 0.33, right? Okay, this one's probably tiny. This one's like 0.0074. So I need to add those together, and that gives me the relative uncertainty in the work. If I add those together, I get like 0.34. All right. If I turn that into percent, like Jake wanted to do, that's 34%. So there is 34% uncertainty in this 0.8 joules. We want to report the absolute uncertainty in that. To get the absolute uncertainty, I have to multiply this by the relative. So 0.8 multiplied by 0.34 gives me 0.27. Right? So my final result for the calculated work is the negative 0.8 joules plus or minus, that has to get rounded to one significant digit, right? Uncertainty should only have one. So plus or minus 0.3 joules. So maybe we did as much as 1.1 joules of work, maybe we only did 0.5 joules of work based on the uncertainty in our values. Alright, so that's nothing new, but it's been a long time since we actually have to process all that. Alright, I'm not going to pause for questions on that. Find an opportunity on Tuesday while we're collecting data, and maybe once we have some new data for us to think about processing. Okay. So the next thing that I wanted to do is just give a little bit more context to the rest of the topic. This branch of physics that we're concerned with, yeah, the unit is called thermal physics, but really this is called thermodynamics. When did we start studying these things like heat and gases doing work? Like how long ago? What century?
1800s.
Yeah, like 1800s, because in the 1800s, like everybody under the sun was trying to build steam engines and internal combustion engines and all that good stuff, right? And this is the realm of physics that goes into getting mechanical work out of our energy-dense fuels. Alright, so this branch of physics is concerned with the macroscopic properties of gases, our temperature, our volume, our pressure. Now earlier in topic 3, right, we dealt with heat. Right? We said that heat can be transferred based on a temperature difference. We said heat goes from higher temperature things to colder temperature things, and that's true. Right? But that's not the only way that we can transfer thermal energy. That's not the only way we can do heat. We can also get heat by doing work to a system or getting work out of a system. So we're going to be looking at some non-mechanical energy. We're going to be looking at kind of heat interplaying with mechanical energy. All right. So we do have like 3/4 laws of thermodynamics. Where we really only talked about 2 of them in this topic. And our first one, I think it's us. Our first one, well, all of them involve our heat. I didn't think it's. It is. Okay, very good. All right, Brian, you are liberated. The first law of thermodynamics is in the data booklet. Right, it's the one that I think says something like Q equals delta U plus W. Is that there? Yeah, great. All right, so the first law of thermodynamics says that we can send heat into a system, and maybe that heat does some work, or maybe that heat does a temperature change, or a phase change. All right, and that's what this U stands for. This U stands for internal energy. Internal energy could be potential energy if we're doing a phase change. It could be kinetic energy if we're doing a temperature change. Right? So we deliver heat to something. It could go into the molecules, or it could do mechanical work to the surroundings. What did I have anything else significant here? Yes. In this topic, we're only concerned with gases, and we're pretty much only concerned with ideal gases. Among other things, ideal gases had, in an ideal gas, the molecules only interact when they're colliding. That means that they're so far apart that they are not pulling on each other. Right? So there is no potential energy. So all of the internal energy of an ideal gas is in the form of kinetic energy, no potential energy at all, right? So if we're dealing with ideal gases, this delta U for a change in internal energy should only manifest as a temperature change. All right, let's keep going. Let's keep going, then I'll pause for questions. So I think we already said all of this, but the capital U is the symbol for internal energy. We talked about internal energy in topic 3, but we never had a symbol for it. Q is our thermal energy, which is synonymous with heat. And then W obviously is our work. What's the unit for all those things? Joules, right? All energies are measured in joules, work is measured in joules also. So this is not only consistent, but this is saying that energy is conserved. We deliver one type of energy to our system, it shows up as other forms of energy, but that total amount has to stay constant. Right? You might remember when we looked at the objective that it said that we did need to recognize that the first law of thermodynamics was the principle of energy conservation. All right, questions about this before we delve a little deeper into specifically positives and negatives? Okay, great. All right, so this is like important. I want you to know this and retain it. All right, important enough that I've animated this stuff like with sound. All right, so let's talk about the signs of the Q first. Q was the energy delivered to the gas. So if Q is positive, that means yes, we're delivering energy to the gas. Right? We are putting energy into our system. If we are removing energy from our system, then the Q would be negative. We're extracting heat. Questions about Q is positive if we give heat to the system, and Q is negative if we take heat away from the system. I think it's pretty straightforward. All right, work we already dealt with earlier. Right? Work is positive if the system is doing work to the surroundings, so if the system expands. And then work is negative if the surroundings do work to the system and the system contracts. Right? We said all of that earlier. And follow-up questions about work being positive or negative. All right, so internal energy is the remaining one. Although I guess I don't actually have that on there. So a positive delta U means that the molecules will have more energy, higher temperature, if we're talking about an ideal gas. And a negative delta U means we are taking energy out of the molecules, right? So we're dropping their temperature. Right? So know it, it's important, but it's also not that complicated. And then this is just a review from what we said a few minutes ago. Internal energy is the sum of molecular, kinetic, and potential energies, but if we're dealing with an ideal gas, the molecules aren't supposed to have any potential energy, so we really do only need to consider the kinetic energy and temperature if our gas is ideal. All right, any other issues at this point on the first law of thermodynamics? We were so efficient in not wanting to get behind that we are actually mildly ahead. Let me turn the camera off, and then I'm thrilled to